The video will look really bad, but yes, वो कर सकते थे, लेकिन यानी जो अगर सामने आप वीडियो रिकॉर्ड कर रहे हैं तो then that looks really bad, so इस वजह से preferably ना इसके ऊपर. Then I don't feel I'm doing justice to the audience, right? Talking, so it's fine. Inshallah. All right, I think we are on time as well, so we're starting 5 minutes later nearly. Assalamu alaikum everyone. Thank you very much for coming to the research talk today. A World Beyond Quantum. I'm Jibran. Announcement: this talk does not require you to know anything about quantum. My hope is that by the end of this session, I have at least communicated to you a brief inkling of why there's much more interest in quantum other than the standard popular description that you might see in popular science articles. Here, quantum computer ka ban gaya. We can do factorization, encryption breaks, and potentially some hell breaks loose. Yes, all that is potentially there as well, but there's so much more to why there is and should be interest in research related to quantum computing and information. And that's my motivation today, to communicate those directions to you without necessarily requiring any background in quantum. So hence the title, A World Beyond Quantum, that there are interesting things to pursue even beyond the boundary of what we know about quantum physics. And let's start right away with the example that I motivated in the abstract. So we've got the Mughal Emperor Akbar, and let's say he wanted to do some computation. And the computation he wants to do is dependent on some information that he already has access to. Being a computer science department and faculty member, we'll represent information as a bunch of bits, x1 to xn, each exabyte is a bit. And this is all the information that he needs to do the computation, let's say, is available to him. And he is, let's say, the all supreme monarch in his empire. So all the computing resources of the empire are also available to him. So he can literally just compute this function over any of these inputs, right? So f of anything over these inputs can directly be computed by himself, right? So there's nothing kind of interesting to say about there for an all-powerful computational device that has access to all information. But things become a bit more interesting if he does not have access to the information. He might be all-powerful and he has a computational question to ask. He wants to know the answer to this question. If again, let's assume the answer is just a yes or no, so it's for the Boolean function. But the information that he needs to compute F is actually distributed between some of his courtiers. Let's say his viziers in the court. So there's some bit string, x1 to xn, some private information that, let's say, this vizier 1 has. I won't name them for political correctness. And then you have vizier number 2, who might have some other sequence of private information only known to him as well. Now, computational strength on Akbar's side won't help him do the computation because the input on which he needs to compute isn't available to him. Now, let's make things more interesting as well, where you could just ask, well, Akbar calls his courtiers, asks them for the information, and they will give it to him. And in a situation where the courtiers don't trust Akbar, let's say perhaps with this information, this may not be possible. Would Akbar really trust, the information that they're giving to him? Let's say we are in a situation where they don't trust communicating that information. In fact, it's even more complicated. The two viziers don't even trust each other, so they don't want to make this information even known to each other as well. So Akbar turns to his trusty vizier, Birbal, asks him, what am I supposed to do? I have a problem, a question I want to ask, which has a simple yes, no answer. But the information that I need to compute this information, this function, this problem, is not available to me. It's available just to these viziers. And I don't trust them. They don't trust me. But I would still like to compute this. And now, because you're bringing in this vizier, it brings in this additional complication as well, right? So just like Akbar is interested, Birbal is interested as well. And you might even make it more complicated. Let's say Akbar doesn't completely trust Birbal as well, in the sense that Akbar doesn't want to let Birbal know the problem that he would like the answer to. Right, so we've got all these requirements that we'll summarize again over here. So Akbar is essentially asking Birbal, hey, here's the problem that I want to solve. I want to compute this Boolean function f, which is dependent on some bit string x hat, which is known to Vizier 1 only, some information y hat, which is only available to Vizier 2. Now, Birbal shouldn't learn the function, the question that Akbar is asking, and neither should Birbal learn the private information that Vizier 1 and Vizier 2 have. Right? That was the initial. Similarly, Akbar also shouldn't learn the private information of both of the Viziers, and neither Vizier learns the private information of each other. And yet, at the end of whatever Birbal would have to suggest, Akbar should have the answer to his function. So this is a dilemma that Akbar proposes to Birbal. Well, let's kind of make things more specific so that we can work through an example. Let's say Akbar wants to know, do an internal audit and wants to figure out, how much wealth does Vizier 1 have and how much wealth does Vizier 2 have. So now you can understand why they would not want to make it public. So even though they might trust Akbar in the sense that if he asks him to do a computation, he'll do that computation, but they still do not feel comfortable letting Akbar know, hey, this is the amount of wealth I have. Yet, Akbar should be able to compute, does Vizier 1 and Vizier 2, let's say, have equal wealth. So that's, for example, the function that we'll try to compute. Let's say Akbar wants to know the information that is known to Vizier 1 and the information that is known to Vizier 2, is it equal? You can give it some storyboard around it, but that's essentially, for our purpose of Boolean function, the job. Going back to our theory of Boolean functions, it's a nice modern version of Mughal Empire. They have the theory of Boolean functions developed. They know, and let's say our information is small, so the information on Vizier 1 side is just 2 bits. The information on Vizier 2 side is just 2 bits. So we've got x1, x2 on one side, y1, y2 on one side. You can extrapolate it to as large a sequence as you like based on kind of the protocol that we'll do. So what would the equal function look like over here? Well, the equal function will evaluate to 1 on exactly 4 input possibilities, right? So when all entries are 0, or, so x1, x2 is 0, 1, y1, y2 is 0, 1, similarly 1, 0, or all 1s, right? So all of from the 16 possibilities, the function evaluates to 1 on exactly 4 of the input possibilities, 0 on everything else. So that's what they'd like to compute. Using a representation of Boolean function, they can take that truth table, compute kind of this monomial over these 4 variables. And so they have this representation of this Boolean function in terms of the 4 variables. Now, what I'd like you to focus on is in this expression, this decomposition is kind of simple in the sense that all of the information you need to compute this term is locally known to Vizier 1, x1 and x2. It's only dependent on x1 and x2. So this entire sequence can be computed by Vizier 1. So you can take that entire computation and replace it again with a single bit, let's say x1 prime. Similarly, this y1 and y2 is something that can be locally done on Vizier 2 side without him necessarily doing any interaction with anyone else. So y1 times y2 becomes another bit string, let's say y1 prime. However, the issue becomes these 2 functions in the decomposition, where now both of these terms are dependent on each other because the parties essentially need to compute the AND function between information that is shared across them. And if without communication between them, without revealing the information to each other, this may not be possible. And that's exactly where we'll see Birbal's strategy will come into play to help in this computation. Right? So the situation then is, you assume, even though these parties do not necessarily trust each other, but because the theory of Boolean functions is known, they have met together even and perhaps agreed upon a universal way to a canonical decomposition of how to write all Boolean functions. Right? So not just for the equal function, but imagine for any Boolean function, they know actually jab aap iski decomposition karenge in terms of our information. This is the canonical decomposition or standard representation of the Boolean function. So they will be able to, each of them on their own side, acha agar main se ye question pucha gaya, ye wali term main locally compute kar sakta hu, aur ye wali term main compute nahi kar sakta. So both of them will have access to this representation of the question that has been asked to them. And then based on what Birbal tells them, so Birbal is communicating this term, hey, you can compute this on your end. You can, Vizier 2, you can compute this on your end. This term and this term I will help you with. But before we get that, so, right, so we have been able to simplify equal into kind of this nicer, simpler looking setting where two terms now are in question, right? What does Birbal do? Birbal now essentially, so recall these bits x2 prime, y2 prime, x3 prime, y3 prime. Birbal now Birbal doesn't know the question. We'll explicitly work through the evolution. But Birbal now tells them, you will get this bit string on your end, Wazir 1, and you will get this bit string on your end, Wazir 2. Send me these individual bits. Once you send them to me, so for example, in this situation, here is x2 prime coming in, here is y2 prime coming in to Birbal. Birbal will respond with a bit, let's say A1 and B1. How will these bits be determined? Those bits are determined by exactly this 4x4 matrix. And this 4x4 matrix is one of the key things that we'll kind of keep coming back to multiple times today. The rows are being indexed by the input possibilities. There are 4 input possibilities. The columns are being indexed by the output possibilities. Again, 4 possibilities because there are 2 bits on each side. Now, each row you will see defines a probability vector. In fact, the terms in this 4x4 matrix can be thought of as defining this probability term. Probability for Birbal to output bit A and B conditioned on receiving input X and Y. And once we have that interpretation, then you see, all right, so in this case, what Birbal is just doing is if I receive 0, 0, I will output 0, 0 or 1, 1 with probability half each. Same applies to input 0, 1, input 1, 0. Things get flipped when you have input possibility 1, 1. There, now Birbal answers AB with parity 0, 1, with value 0, 1 or 1, 0. In other sense, in this situation, the parity of Birbal's output is odd with a uniform distribution between the 2 possibilities. And in these remaining 3 possibilities, the parity is even for input 0, 0, 0, 1, 1, 0. Now, the structure of this matrix actually could be nicely represented as just this criteria. What Birbal is actually doing is saying the parity of my output bits will equal the AND of the input bits. And if you recall the last slide where we were doing the computation, the issue was exactly this, that the term in the equal function that the 2 wazirs needed to compute had an AND in it, right? So there was this X prime and there was this Y prime. However, now if Birbal sends an A to Wazir 1 and a B to Wazir 2 with the property that A parity B will equal X and Y, what the 2 can imagine is happening in their equal function, these terms x2, y2 prime can now be replaced by A1 prime, A1 and B1 that they received from Birbal. Similarly, the x2 prime, y2 prime can be replaced by A2 and x3 prime, y3 prime in this case can be replaced with A2 parity B2. So again, the issue becomes that this AND, which cannot be computed by these parties without communicating with each other, has now been decomposed into 2 bits such that each party has 1 share of that bit such that the required constraint is still satisfied. Hence, the entire equal function, which had this form, now will have just this form, where note that this A1 parity B1 is the replacement of x2 prime, y2 prime. A2 parity B2 is the replacement of x3 prime, y3 prime. And once you have that, then this entire expression actually becomes decomposed into kind of something that Wazir 1 can compute locally, parity, something that Wazir 2 can compute locally. Hence, you can write it as A parity, something, a bit that Wazir 1 computes, and B prime, something that Wazir 2 computes locally. Once they have this A prime and B prime, they just need to send these bits back to Akbar. And Akbar says, all right, I know how to compute the parity function for sure. I compute A parity B, and that's exactly the output of the equal function, right? So to recap, Akbar wanted to compute equal function. So he communicates, hey, give me the computation of the equal function on your private information. Birbal strategy dictates that after viziers have figured out the Boolean decomposition, the canonical representation, Vizier 1 communicates x2 prime and x3 prime, and Vizier 2 communicates y2 prime and y3 prime. Based on this, Birbal communicated back to the two viziers, A1 and A2, B1 and B2, with the required property that A1 parity B1 is equal to x2 prime and y2 prime, and same thing for A2 parity B2. With these bits of information, the two parties now are able to compute these things, which then result in Vizier 1 sending back A prime to Akbar, Vizier 2 sending back B prime to Akbar, and finally this just becomes A prime parity B prime. And so all the requirements that were laid out for Akbar are satisfied. And so Birbal has again kind of become kind of leveled up in Akbar's code. Any questions about?
These primes are independently distributed, x and y, x prime and y prime?
They will naturally depend on the decomposition of the specific Boolean function under consideration, right? So
no, we are computing this by using probability. So are they independent?
So based on, so what you can look at this matrix is that this is a uniform distribution over the received xy. So if you fix an xy, the received outputs A and B follow a random bit. So what you can do is actually ask, well, given that Vizier 2's bit is fixed, what is the distribution of the bits value on Vizier 1 side? And you can show that it will be just a uniformly random bit and vice versa.
So it means that x and y both follows normal distribution?
यहाँ पे तो single uniform distribution है ना दोनों के दरमियान. Uniform है. It's a uniformly random bit. It's a perfect fair point flip. That's it. It's a perfectly fair point flip. That's all that they have for a single bit. Independent of what? So x and y will in general be independently distributed. If they are correlated for some specific choice of f, then because for some specific choice of f, the correlation in that function might require that x and y have some specific pattern, but in general, they will be not correlated together. We'll come back to this requirement actually more explicitly soon. Any questions about the protocol itself, though, in terms of how it is satisfying the requirements that were laid out? And would you agree that it satisfies the requirement laid out more or less? You know, ho sakta humne concrete kind of technical analysis of security to nahi kiya, and there wasn't like, you know, hardcore encryption going on over here. It was just all of the discussion really delves upon this little simple 4x4 matrix that follows a very specific rule. I haven't really been motivated where this rule came from or why we are interested in it, but just that if we had access to this advice, or if someone is following this advice, then it is possible by following this advice to do really some interesting things. Right? So that's the takeaway so far from the discussion.
Is it possible for the state Akbar to conspire with people to find out the information that is locally available?
For sure, you can now modify the setting and say, well, all right, can I, you know, given the choice of function that I was computing, or given that we follow this experiment multiple times for different choices of f, do I become, you know, more, you could have a function which is literally just equal to the input of, you know, f of x comma y is equal to x, right? So for sure, those kind of cases are there, but you know, in that case, Vizier 1 already will say, hey, wait a minute, this is not satisfying the requirement of what I told you. I will do the thing for you as long as my private information is not revealed. You're asking me a question that will reveal the information to you directly. So hey, all bets are off in that sense, right? So yeah, so it's not all there in that sense, but still we've got kind of a hand-wavy idea of something interesting happening here. And we'll motivate that to building towards a more general framework. Since this 4x4 matrix that Birbal kind of followed was the key point of interest, let's try to investigate that a bit more in depth. So as I mentioned, it's a 4x4 matrix where each row is a probability. It's a joint conditional probability distribution. So sum of each row will equal 1. All the entries naturally also greater than equal to 0. And that's the key object of interest. And the way we'll now bring in quantum into all of this and our discussion regarding computation and whatnot is to ask, well, is Birbal really possible? And actually, can we implement Birbal without actually there being an actual Birbal there? i.e. can he be automated in some sense? Automated actually in a stronger sense that both the parties, Wazir 1 and Wazir 2, don't actually need to communicate with some third party. They just have something in their own palace, in their own house. So Wazir 1 has a small box in his house. Wazir 2 has a small box in his house. He puts in X, gets an A out. The other side puts in a Y, gets a B out. And somehow they are correlated in such a way that this property that the box had would be satisfied. Now, naturally, we will investigate exactly what is possible and what is not possible. The closest thing that we already have in classical computation to this, we would say, well, there's public randomness and private randomness. So Wazir 1 and Wazir 2 could have met together and just flipped lots of coins, and the bit string that they generated together would be the public randomness. Or just sitting in the palace, they say, all right, let's flip coins randomly in my house, and that would be a private randomness. So you could ask, well, do public and private randomness put together allow the two Wazirs to simulate this box? And what we'll build up to is, well, if that's not possible, hint, that's the suggestion, it's not, does quantum mechanics allow that? And if so, why? If not, why not? So, but before we get there, the way I want to kind of structure it is first, we take the rule that was on that probability distribution, right? So you had this issue where you can now look at the setup as Wazir 1 gets an input X in some sense, Wazir 2 gets an input Y. Think of it in this one. So it's slightly equivalent, but slightly different way of what we just computed, rather than Wazir 1 and Wazir 2 generating this themselves because they had it. Let's assume this X and Y is being given to them with a uniform distribution. So X uniform and Y together, the four possibilities are uniformly randomly generated, and they will now need to produce some bit A and B as outputs. And so we're interested in this P of AB conditioned XY as the mathematical entity that will describe their behavior. The key constraint that we need to enforce between them is this issue of, in some sense, what you could say, hey, that there is going to be no communication. It doesn't need a line in between. All right. That there is no communication between them. Via this no communication constraint, what we are essentially enforcing is that Wazir 1's input should not be known by Wazir 2, and Wazir 2's input should not be known by Wazir 1. And we'll spend a little bit of time figuring out how exactly should we encode this requirement. This actually is not as simple as a standard classical requirement of, hey, these need to be independent distributions. Also, so P of AB conditioned XY equals P of, oops, change my pen. P of A given X times P of B given Y, right? So that's the standard way you would say, well, the two distribution on the two sides are independent, so they admit this decomposition. For sure, if they admit this decomposition, then you will have this issue satisfied of no communication between them. But it is a stricter requirement than the more relaxed requirement that we have, that based on whatever happens on Wazir 1's side, Wazir 2 should not know about the information of Wazir 1 and vice versa. So what constraint actually enforces this requirement? And that's what we'd like to label as the no signaling conditions, and what's known in the literature. So no signaling conditions are going to be our formulation of this intuitive requirement that whatever happens on one end should not influence the statistical distribution on the other end. Stated like that, it almost kind of seems straightforward to write it as, well, okay, Wazir 1's marginal P of A given X should not be influenced by whatever happens on the other side. To begin with, this distribution, this marginal distribution, by definition, is this thing, right? So sum over what happens on Wazir 2's side over the joint conditional distribution, and I get Wazir 1's marginal distribution. But if I now, so this thing is the definition, this thing is the constraint that I will enforce as no signaling, that this thing should equal or should not depend on how Wazir 2's input changes. It doesn't matter whether Wazir 1's input was 0, or whether Wazir 2's input was 0 or Wazir 2's input was 1. the marginal on Wazir 1's side is independent, it does not get influenced. The statistical distribution, the probability distribution that Wazir 1 is able to generate on his side is independent of the input that Wazir 2 receives. And so that takes care of one side of the communication. You again similarly impose the other direction where you say P of B given Y, the marginal on Wazir 2's side by definition is something that we obtain by taking the sum over Wazir 1's outputs in the joint conditional distribution. And then the constraint part of it will be that, hey, this thing should equal the same definition, but if I change the X to some other entry. So if Wazir 1's input changes, Wazir 2's distribution should not get influenced. So we will take that as the key constraint enforced by this box that Birbal was, by this distribution that Birbal was following. That what I do should not allow each of the other side to figure out what the other party's input was. So you can take these constraints and kind of visualize them also as essentially a bunch of 8 constraints. So you can expand them out. So for example, if I write one explicit term over here, this could read something like the form P00 given 00. So since I'm summing over A, it will be now P10 given 00 equals, now in the left-hand side, I had now fixed X, so to be, this is right? Yeah. So in the other case, I will now sum over again A, P00. Since I was summing over A, Y is the thing that has to be changed, 01 plus 10 given 01. In general, what these constraints would look like are that in that 4x4 matrix, the sum of these 2 entries has to equal the sum of these 2 entries. The sum of these 2 entries have to equal the sum of these 2 entries, and so on and so forth. So it's just a bunch of linear constraints. In this situation, 8 constraints on this 4x4 set of probabilities. Right? So there's computationally, it's very easy to enforce. What we can ask now then though is, what kind of world do we live in? One situation is where we say, hey, let's take Birbal's strategy and implement it as is. Let's assume we are living in a world where there does in fact exist this box that you could purchase at your local tech store, such that Wazir 1 will have it as on his end, Wazir 2 will have it on his end, even though in this picture it's shown as one box, just so that you could have the rule inside the box. But imagine that physically, it will be one box on Wazir's end, Wazir 1 side, Wazir, and the other box on Wazir 2 side. So there's nothing that's directly linking them together, per se. And that will be a key issue when we will connect them to physical consequences. And this box follows this property, which we highlighted in Birbal's strategy, that the parity of the outputs equals and of the inputs, and that there's a uniform distribution over there. Right, so that's kind of what's called the perfect non-local box. And if you look at this matrix, the one way to define a measure of how well such a given strategy works is to basically just say, hey, sum over all the 8 probabilities for which the rule A parity B equals X and Y is satisfied, and then negate from it the sum of all the 8 probabilities for which this rule is not satisfied. This becomes one very simple kind of L1 norm measure on how well this distribution or this strategy that a box might be implementing satisfies this rule of A parity B equals X and Y. Naturally, the box itself, by definition, perfectly satisfies this requirement. Right? So you just recall the probabilities are just half on each of the events that satisfy this criteria. You sum them up, you get 4 over here, you get 0 over here because there's 0 on all the entries that don't satisfy this requirement. So this value for this box becomes 4. Now, going to, can classical physics allow this? Without going into the details, what we know is that if classical physics wanted to simulate this correlation while still enforcing the no signaling constraint, so that's the key constraint that we want to enforce. What you can show is that in the classical situation, this value will have to be less than or equal to 2. So we are way off in being able to simulate Birbal's strategy without communication. You could ask now, well, what if the two viziers, rather than having just classical shared randomness, had this fuzzy notion of quantum entanglement? They had a quantum entangled state shared between them. And in that case, you can show that while, yes, they can do better than quantum, than classical, they still are far off from what was possible with the perfect non-local box. So 2 is the bound on the classical world, 2 square root 2 is the bound on the quantum world, and all the region between 2 square root 2 and 4 is something that we kind of don't really understand well enough. So then the question asked is, wait a minute, the physical structure that we had, the only constraint in that experiment that we had was this no signaling requirement. How is it that physical reality or a theory of physical reality somehow disallows correlations that satisfy this no signaling requirement? What other requirements, what other principles or constraints are there on physical theories, on nature of reality, that cause it to be bounded by something lower than what the non-local box allows? That's one key kind of struggle or question in this research direction. The way you can imagine it is, you take that P of AB given XY, that entire 4 by 4 matrix, and imagine the space of all possible 4 by 4 strategies. So PAB, condition XY, and all the valid probability distributions that are valid for probability vectors. And now do a 2-dimensional projection of that entire space and say, define for me the boundary of what is allowed by classical physics. And this square is, for the moment, what you can imagine is what classical physics allows. So that bound that you have of that value is less than or equal to 2, you can imagine this hyperplane is this bound, B is less than or equal to 2. Now you say, well, wait a minute, what does non-signaling look like? You can similarly consider the 2-dimensional projection of that entire space of no signaling correlations, and that looks like this. So it is strictly larger than what classical physics allows. There is this point over here, which goes back to what we define as a perfect non-local box. What is interesting about this as well is this non-local box is a single point which will satisfy the requirement that the value that we have defined equals 4. Recall that the non-local box had a uniform distribution over all events that satisfy A parity B equals X and Y. What this point structure is suggesting is that if you deviate from that uniform distribution even slightly, then the box no longer is a no signaling box, and hence it won't be in this red kind of polytope, red region. It will go beyond that region because that correlation being generated has become a signaling correlation. So being that uniform distribution was necessary for it to be signaling. But if you go below 4, if you move below here, then yes, the lower you are, the more freedom you have in deviating from a uniform distribution. The point of interest being what actual physical theories are possible, then the only key generalization that we have is quantum physics. And what's known is that quantum physics, one of the best theories of nature and reality that we have, somehow ends up being nicely sandwiched between the two. So you've got classical physics below. The historical evolution and development of quantum mechanics actually framed this separation between the classical and quantum world as something that's perhaps a paradox. This is what you hear when you see in popular descriptions in quantum mechanics that quantum mechanics is non-local. What they're referring to is this possibility of the quantum region going beyond what is possible classically. But here what I'm motivating is something more kind of interesting in a sense that there actually is a region even beyond quantum. That quantum physics, the current theory of physical reality that we have, doesn't allow, even though that theory does admit or satisfy the key physical constraint that we had in the experiment under consideration, i.e. the no signaling constraint. So you can come up with an experiment and then you enforce the key constraint in that experiment via the no signaling constraints. And then you say, all right, here's a correlation. Here's an experiment. Here's a distribution that I should be able to see as output of an experiment because it satisfies the no signaling distribution. But quantum mechanics comes back and tells you, no, I will not allow you to develop any experiment in the lab that will allow you to generate this distribution. And what you can then ask is, well, if that's not the case, there are two possibilities. Either our understanding of quantum mechanics is incomplete, there's an additional constraint at play that we haven't been able to formulate yet on physics, that is lowering this bound of what quantum mechanics allows, or there is, as of yet, undeveloped theory of reality, which actually generalize even quantum physics, just like quantum physics generalize classical physics, right? And so people have investigated this direction for the last kind of 30 years or so, and there's lots of knowns. So what this triangle you can think of as us zooming into this direction. And as we identified that this point at the top is the perfect non-local box, this here bound over here is that bound that we had of v is less than or equal to 2. This kind of, if you were to draw a hyperplane here, would be the quantum bound v is less than or equal to 2 square root 2, but the quantum region is more interesting. It's not just defined by the single hyperplane. It's a convex region, but it's not a polytope. So you won't have like finitely many vertices for it. Rather, it's this region that falls off. And the exact characterization of this bound itself is also an interesting and partially developed result. It's not completely known yet. And in fact, when we talk about what exactly could be a possible generalization of quantum mechanics to figure out new theories of reality, what we're actually talking about is exactly, well, could we do a perturbation exactly at this bound such that you get something that is almost quantum, but is still beyond quantum? And so that direction hasn't even been investigated in the literature. And you talk about now stuff that is completely outside of my expertise zone, where you say, all right, you're doing an experiment near the boundary of a black hole, and some of your information drops in the black hole. This is not exactly the black hole information paradox, but work that is built upon it. And you say, well, okay, perhaps exactly at the boundary of a black hole, where GR and quantum again come into play together, you could have correlations that somehow are so exotic that they'll go beyond the bound of what is not currently known to be possible via quantum mechanics. So that's one possibility. And so people coming in from physics, from computer science, from cryptography, security, have looked at this picture in many different ways to figure out why exactly is quantum mechanics being bounded by this kind of plane over here. To this date, it's an open kind of question. We don't have a complete characterization of this result. Part of this result is what we are also working on at IBA. And so the situation is kind of like this, right? So just like an investigation of science, no one really knows a complete picture yet. So everyone is kind of looking at their kind of expertise zone, and based on their expertise, they realize that, oh, well, it looks like this, so this principle must be enforced. Oh, no, it looks like this, so perhaps this other principle is being enforced, but we don't have a complete characterization really. And so, ideas are welcome about what really could be at play over here. So a couple of things before I move on to the final bit. So the current investigation in this research direction, one I already mentioned, almost quantum correlations, where you say, all right, what if I'm at the boundary of the currently known quantum region and perturb slightly at that region? Could I get something that is beyond the known quantum realm, but still physically possible? So that's one direction that's being investigated. The one direction that we are looking at in detail with an IBA is that if you now go back and say, well, I want to generate a principle that identifies, that imposes the constraint of what is the boundary of quantum mechanics, then what is known is that no bipartite principle can be such a rule. What do you mean by bipartite principle? Basically, just like the situation we considered between Akbar and Birbal and Aziz, that there are only two parties at play. You can take that distribution and consider it between kind of two sections or two groupings. So you could have multiple parties at play, but you still consider, well, okay, I'll consider this one two-party group or this two-party group. So you can take any multi-party group you like and consider two-party decompositions. What's known now then is you could generate these larger party distributions, 5, 6, 7 parties, such that that correlation is stronger than quantum. But when you take this bipartite marginal of that bigger correlation, right? So you had something defined over all the 5 parties, but then you said, let's clean up the picture a bit. I want to look at the specific marginal of these 2 parties within that bigger 5-party distribution. Then even though the bigger 5-party distribution was stronger than quantum, any possible bipartite projection of it will actually not just be quantum, will actually become classical. So you've got the situation where in the multi-party case, you're stronger than quantum, But in the bipartite case, you kind of jump over the quantum region and become purely classical. Hence the claim that if you come up with any kind of bipartite principle, you will not be able to distinguish or come up with this key criteria of identifying exactly quantum correlations, because this bipartite principle will fail to identify this multipartite stronger than quantum correlations, because their bipartite version or their bipartite version is actually classical, right? So this is something we are investigating, but there's a long way to go. And so what we have shown so far today is one example of how quantum mechanics, even though has lots of cool stuff in it and interesting discussions to be had about many aspects of it, is not the final say on things. There is a world beyond it to investigate, both experimentally and theoretically. And the final word hasn't been written in terms of whether what you investigate theoretically could actually indeed in principle end up being a physical reality as well, in terms of become an actual theory of physics. However, I won't leave you just with that. I will leave you with kind of the other direction as well. So even though one argument is quantum somehow is less restrictive, but you can now ask another problem. We were looking at one kind of computational model, i.e. of communication complexity with some security stuff thrown in. Now you can go back to a different model, more computationally motivated, and come up with an interesting distinction there. And so for people who might not have kind of seen this before, very kind of quickly, what do I mean by P over here? P is a label for all problems that you can solve on sitting on your laptop in polynomial time. P space is a class of problems that you can solve in polynomial space on your computer. Exp is a class that you can solve, the class of problems that you can solve in exponential time. Next is non-deterministic exponential time. There's a reason why I'm giving you kind of this crash kind of summary of these labels. I assure you there's a point to it, otherwise I wouldn't have done it. And non-deterministic, if you haven't really thought about it a bit over here, think about it as deterministic problems for which there is a possible way to verify the solution, in this case in exponential. And so when I say next is the class of problems for which verification of the solution is possible in exponential deterministic time. This kind of relates similarly like how you have P and NP. Note I haven't really defined NP over here because I don't want to talk about it right now. But the key open problem in theoretical computation complexity is P versus NP. P is a problem or set of problems, class of problems solvable in polynomial time. NP, class of problems solvable in non-deterministic polynomial time. But for your intuition, you can think of them as class of problems for which you can verify the solution in polynomial time. So jahan bhi aap computation ke non-determinism dekhna, one nice way to build up your intuition is to think about it as a verification problem. And you can translate it to a deterministic variant of it. But one problem, even though you might have heard of these classes, one you might not have heard of is this IP. IP is this class of problems called interactive proof. And this is what we want to talk about a bit in terms of its connection with these other classes that you've just mentioned. What is IP? IP now allows you to go back in the communication setup that we're thinking about. And now the constraint is Birbal is this all-powerful computational prover, and Akbar is a polynomially bounded verifier. So it's a different setup that we were considering previously. Akbar has some computation that he would like to do, but Akbar just doesn't have the resources to do it. In your modern day setting, it's kind of like, you buying some time in a high performance computing lab, let's say, so that becomes your kind of, computation server, and you're a client, you have some computation that you would like to do, you can't do it yourself, so you'll ask someone to do it for you. But then the issue also becomes, do you trust the person who will do that computation for you? And so the multiple different variants you can think of here in interactive proof systems, what we are thinking about is prover, in this case Birbal, computationally unlimited, verifier, polynomially bounded. Is there an interaction between the prover and verifier such that the verifier, given their limited computational ability, still get convinced that they have found the answer to their problem, or with very low probability will not be kind of misled? So I won't bore you with the technical details, but just the idea. So imagine, for example, go back to your standard factorization problem. We don't have an efficient algorithm for factorization. Akbar wanted to factorize a number. Rather than factorizing himself, Akbar gives this number to Birbal. Birbal factorizes it for him and just gives him the factors. Akbar doesn't have to trust Birbal. Akbar can just multiply the integers out together to verify, oh yeah, multiplying is easy to do. I can do that smaller, intensive computation on my end, and multiplying them out indeed gives me the original number I had. Hence, this factorization of the number is correct. But this is a problem in NP. IP actually is a much bigger class. So what's known is that IP actually equals P space. And P space is thought to be much bigger than just P. In fact, now though, what we are interested in is we can generalize this as well. Rather than one prover, you can have lots of provers. I don't want just one server with computational ability. I want lots of servers with multiple computational abilities. And now what could also happen is that these servers could also talk with each other. So MIP is now that same old interactive proof setting, but with multiple provers. But with these provers, they can also communicate with each other. And now going back to kind of our consideration from the beginning, how they communicate or what kind of resources do the provers share among themselves becomes kind of interesting as well. So I lead you with, apologize if you don't like this way of presenting it. I will leave you with just a sequence of results that has led to something that people totally didn't expect will happen. So what you could ask, for example, now is what happens if the provers are sharing an entangled state between themselves? What if the provers are sharing a non-local box among themselves, and so on and so forth? So what was known is, as I mentioned, one's classical result to start off with is IP equals P space. That was generalized to actually QIP, that if the prover is quantum, so the prover we said was computationally unlimited, all powerful, but classical. But if you make now the prover even quantum, that actually apparently in this situation doesn't help. So quantum prover is the same as classical prover in this setting. So QIP also equals P space. But what you could also show is that MIP, the classical proof system with multiple provers, equals next. So non-deterministic exponential time, which is thought to be is larger than E space. So you would expect if I now give these multiple provers more ability, I allow them to have entanglements between them, I'll allow them to even go and share non-local boxes between them, they will keep getting more powerful. But what people were able to show is that if I give these MIP provers more power in some sense, by giving them access to non-local box to correlate their results, they actually somehow become apparently less restrictive, less powerful. Multiple provers with non-local box to correlate themselves actually is just in deterministic exponential time rather than non-deterministic exponential time. So apparently it becomes restrictive. And the intuition there is kind of like the ability to cheat by the provers actually becomes restricted because they are now correlated so strongly among themselves. But this still remains open, the key possibility of what happens for quantum multiple provers. For a single prover, we already have this. Now, if I go, and this was an open question for like 14 years, people started working on this in like the 2000s as a MS thesis and just couldn't make progress. And here are the sequence of results that came out. So you had P space shown to be in MIP star. MIP star, no. MIP star now is a quantum variant of multiple provers, but with potentially unlimited entanglement shared between them. And here's the kind of key kind of issue. Quantum here, but potentially unlimited entanglement in the pass module. So they have as much correlation generated from a quantum source as they would like. And this built into over time, you'll see hopefully why this sounds so weird and cool. Next was shown to be in MIP star. And people for the most part believe that quantum computers don't allow you to do anything in principle in terms of computability that classical computers already don't allow you to do. So complexity theory se fark padega, but computability theory change nahi hogi. But then the next year people came along and said, that's not a typo, I meant to have two E's in between. So this is non-deterministic super exponential time. So not 2 to the n, but 2 to the 2 to the n, and non-deterministic. So non-deterministic super exponential was shown to be still in MIP star until eventually the final key result came out about a year and a half ago, where they showed MIP star actually equals RE. And RE is a class of recursively enumerable problems. Why is that interesting? Is because that class actually includes uncomputable problems. So the halting problem, which is an uncomputable problem classically, is in RE. And what this result is now showing or claiming is that multiple provers with potentially infinite entanglement can solve the halting problem for a polynomially bounded verifier. And that totally is something unexpected and came out of the zone which no one expected. Naturally, with kind of this, over the last 3 years, as people were building up this hierarchy, people were like, well, wait a minute, how do we exactly kind of bound the strength of MIT star until eventually you get this? So now the whole big picture idea over here, why pushed you through all this, contrast this with what kind of the major part of the talk was about, that there are correlations in this communication kind of setting where there are correlations that can be outside what quantum allows. Yet somehow nature is indeed very subtle, such that when you go to a different kind of computational model, quantum mechanics is just exactly the theory that apparently in some situations is even allowing you to do something that's not even classically computable. So in this perspective, and the jury is still out in terms of how to, the folklore and the general understanding within kind of the scientists would be, this is not saying that you can actually build a computer or a protocol that in practice will solve the halting problem for you, but at least still in principle now you've got a statement of the form, a quantum resource allows you to solve something that is uncomputable classically. And this, in fact, for people who are coming in from mathematics and algebraic operator algebras, there was an open problem of Cohn's embedding conjecture that actually was falsified via the proof of MIT star equals RE. And the details of that, we spent one last graduate seminar last fall trying to work through that proof, and we only went halfway through it. So hopefully we'll kind of try to make more progress this fall as well. So if you're interested, come talk to me. And with that, I'll finish the talk for today. Thank you very much for your patience and interest. Questions, queries, concerns?